Gracias.
Hello, hello. So we start? Let's wait.
Tengo media hora de verdad, ¿no? No, pregunto, ¿por qué no sé? 20, 22. Media hora está bien. Como tú dices. Sí. No, no, por mí está bien. No sé. No me acuerdo. Sí, qué confusión. Sí, sí, lo firmo yo.
Okay, hi everyone. So today we have Marina Manganaro. She's a postdoc working in MAGIC. She came to the IAC in January 2014. Before that, she was a PhD student in Grenoble, where she was working in the European Synchrotron Radiation Facility. She completed her PhD in 2009, and later she moved to Bonn, where she was working in the University of Bonn between 2009 and 2011. She was a particle physicist at the time. She was working on mesons photo productions until then, and then she moved in 2011 to Cork in Ireland to work in the Tyndall National Institute. This is an institute for photonics and solid-state physics. And after then, she came to the IAC in 2014. As I said before, she's a postdoc working in the MAGIC collaboration, where she's doing data processing and data reduction, and she's also working in the scientific exploitation of this data. So she's working in groups related with fundamental physics and dark matter searches. And she's going to talk today about MAGIC and she's work in this collaboration.
Now? Better now? Okay, well, I will just talk very loud, okay? Okay, now it's working better, right? Thank you, yeah, now it's perfect. Okay, everybody, I'm part of the astro particle group in IAC. I don't know if you know already about this group. We are a small group. Our boss is Ramon Garcia Lopez. Then we have Monica Vasquez, another postdoc from Ramon y Cajal. Then it's me working in this group. And also we had another postdoc, Diego, that now is working in Italy, and the PhD student, Rosa Clavero, that now completed their PhD, and soon we will have another PhD coming. We are a small group, and we are working on several experiments on astroparticle physics. But today, I will talk to you about my work that is focused on the MAGIC telescopes. What I will talk to you about are gamma rays from the universe's middle age. And okay, this title, as you can see, we are talking about pushing very high energy astrophysics boundaries. Now, actually, what we done with MAGIC lately, very important results that we had, is that we discovered some sources at the redshift close to 1. Of course, I didn't put this in the title because for you, redshift 1 is just nothing. You probably are working with redshift very, very high. But for very high energy gamma rays, there is the topic of MAGIC telescopes. A redshift like 1 is incredible, a really huge redshift. But I didn't write redshift 1 because you were not here right now, probably. We're still like, okay, 1, I don't care. So why redshift 1 is so important for MAGIC. In very high energy astrophysics, that is the physics we are doing with MAGIC telescopes, we have a limit that is defined by the so-called gamma ray horizon. When you are observing your sources with a lot of different telescopes in other energy bands, you don't have this restriction that we have, because in particular, when we are studying particles coming from the very far universe, we have to consider that these particles, to reach us, they have to travel a lot, and due to their high energy, they can interact with the extragalactic background light. When this happens, all these very energetic particles, gamma rays, they will lose part of their energy. And so when they will reach the ground where the MAGIC telescopes are, we will not detect all the energy of the beginning, the energy that they had at the beginning, but what we see is something that is, of course, lighter and very different. And we have to understand this difference between the original energy and the energy we can see now. And so this means that we have a limit beyond we cannot see any more gamma rays, because these gamma rays coming here to the ground, they are not possible to detect really. And this concept is the so-called gamma ray horizon. And here you can see it is described by a very complicated formula. But all of this just means that beyond the gamma ray horizon, the universe is like opaque to very high energy gamma rays. In this plot here, you can see as the gamma ray horizon was predicted, of course following this formula, and you can see all these blue lines are the different redshift, and increasing this redshift, we can see here that after that we are going, in energy that are more and more and more lower. This red line here is is where the optical depth is equal to 1, and at this point we consider, and this is a way to depict the gamma ray horizon. Also here you can see another plot that is plotting the gamma ray horizon predicted. There are different blue lines here because it's the changing of the Hubble constant, but in general what I wanted to show you is the shape of this so-called gamma ray horizon. And this, the horizon was also measured, and you can see here a plot from a recent paper by Dominguez et al. You can see that using this prediction, it is possible actually to calculate this horizon using data from AGNs. And here in this plot, you can see that redshift close to 1, we don't have enough data. In very high energy gamma rays, it is very complicated to detect AGNs with and redshift so high. So when this paper was published, the highest redshift source was here, and data from one redshift, they are missing. Here you can see the very high energy gamma ray sky populated with all the sources that have been discovered by MAGIC, but also by other telescopes working in this energy range. You can see that we detect with MAGIC flat spectrum radio quasars, 5 and probably 6. Here you have the list of the flat spectrum radio quasars discovered by MAGIC. And these last ones here, they are very close to redshift 1. We have this one that is gravitationally lensed, and the last one, PKS1441, that was not the farthest one, because this one is actually an higher redshift, but for this source we could detect such a huge flare that we were able to work on the extragalactic background light, because you can maybe detect a very far source, But what is very interesting and challenging is to study how this light coming from this source is deabsorbed by the extragalactic background light. And to do that, you need to have a good sample of data to work with. Otherwise, it's not easy to analyze and to understand what's going on there. Well, I will tell you later. Yeah, but I can tell you right now that MAGIC has a very high sensitivity, so it's able to have a very low threshold. And this means that it can really see at a very high redshift, because it is depending on the threshold. But I will tell you about this later as well. Okay, what is a flat spectrum radio quasars? Probably you already know that. For us, they are very interesting source to study, because of course the very high energy is not a lot investigated. So we know the spectrum and other energy bands, but for the very high energy part, it is very important to try to understand what is going on in these sources. They present a very high variability, so they are also very interesting for us to study for this reason. And using very high energy, it is possible to understand the region of emission of these gamma rays, for example, and try to understand better how the accelerated particles are produced there. Some time ago, we were talking with some students at the university, and Artemio Herrera, there is also in our group, but I didn't tell this before, said something that I really liked a lot. He said that it's like there is this big monster, no, that carries all the information about the universe, and very high energy is like the tail of this monster. You really do not see everything, but you see a small part, and you want to know more, and you are also a little bit scared, but anyway, it's exciting. And here you can see two astronomy diagrams about these sources we recently detected with MAGIC. Redshift, almost the same, 0.94. For us, it's like, whoa, redshift 0.94 is close to 1, yay, but you know, it's just because it's very high energy. So we published these two astronomers' telegram calling for other multi-wavelength observation, but before us, Fermi, that is another important partner of MAGIC, discovered the high energy photons from these sources, so they pushed up to follow this observation. Yes, I will talk about MAGIC telescopes a little bit. You know, they are in La Palma, in the Roca de los Muchachos Observatory, and they are the most beautiful telescopes there. Okay, just because they are covered with mirrors, and they reflect all the landscape and of course the sky during the night. But okay, what is important here is that they are Imaging Atmospheric Cherenkov Telescopes, so they have a very special way to detect particles. They have a very nice energy range from 50 GeV to 10 TeV. And why this is so nice? Because 50 GeV is a very low energy threshold. It means that you can detect very high energy particles when they are coming really from a high redshift, like close to 1, and decreasing the threshold. You could probably try to go beyond the 1 redshift and see something that is more far away. But okay, we will see this. And also the sensitivity is 0.6 of the Crab Nebula flux, that for Imaging Atmospheric Cherenkov Telescopes is a very great value. And we are working on particle acceleration in most violent cosmic environments, but we are also working in dark matter searches. We are analyzing AGNs. We have several working groups in MAGIC that involve a big number of researchers from all around the world. Now, what really we are detecting? We are detecting light, of course, but very high energy gamma rays. What does this mean? You have all these particles coming from a faraway galaxy then they are traveling through the extragalactic background light that is filling all the universe. Then they interact with the photons of the extragalactic background light. They produce a couple of electrons and positrons, and at the end, they reach the atmosphere when they produce more and more pair of electrons and positrons. So what we see at the end? What we see is like an electromagnetic shower that is detected by our telescope. So we don't see, you know, beautiful images like the Hubble telescopes or stuff like that. What we see are the Cherenkov light produced by all these particles when they interact with the atmosphere, and they are slowed down by the atmosphere. And you can also say, okay, but what you see, this shower of particles, is coming from a gamma ray or is coming from another particle? Because it could be produced by a proton or by something else. So how could we decide if what we are seeing is coming from a gamma ray or is coming from another particle that we don't want to analyze right now? We can check the shape of our shower. You can see here the shape of electromagnetic shower that is produced by a gamma ray, and here on the right, the shower produced by an hadron. It's different. The shape produced here is clearly different, so we can analyze that and discriminate between particles. I will show you another simulation here that is maybe more clear. Here we have a gamma ray of 50 GeV, and this is the shape simulated of the electromagnetic shower produced here. And in this small square, you can see the projection on the ground. So it's more symmetric than the one produced by a proton of 100 GeV, for example. So working on this difference and with the so-called Hillas parameters that define this difference, the MAGIC telescopes are able to understand the gamma rays, to discriminate between gamma rays and the background. And this discrimination is actually working very well. So we are able to really detect, to really not get rid of the background, but really we can make a very clean analysis with that. Okay, the Cherenkov radiation, I was talking a little bit about that before, but here you can see more information about that. It's emitted whenever a charged particle traverses a medium at a speed larger than the one of the light in the medium, and this is what happens when these charged particles are traveling through the atmosphere to be detected on the ground by the telescopes. And we can work with Cherenkov radiation, of course, and we can detect it basically using a photomultiplier. Photomultiplier are all, the camera of MAGIC telescopes is made of 1,000 photomultipliers that can detect this Cherenkov light. So, in summary, what I just want to tell you is that what we see is completely different from what can be seen by other telescopes. And this is a little bit frustrating from one side, but from the other side it's extremely interesting because we can really go and work on the limit of the energy, with the highest energy that is possible to detect on Earth. And yes, here you can see another sketch of what the Imaging Atmospheric Cherenkov Telescopes does. Here we have just one telescope, just to explain better this concept of the detection for MAGIC. You can see here there is an electromagnetic shower, and the mirrors of MAGIC reflect all this light, and then this light is detected by the camera. The camera here is made of a lot of photomultipliers, and the photomultipliers, of course, they can tell you where the light is coming. They can show you the shape of this electromagnetic shower, that at the end is like an ellipse or something like that you can see in the camera. When you are working with more than one telescopes, then you have an array. In this moment, MAGIC is composed by 2 telescopes working in stereo. In this case, of course, you can better define the position of the light you are detecting. You can better analyze the morphology of the source because you have more information about where the photons are coming, reconstructing better the positions. And here you can see a plot of MAGIC sensitivity that is increasing over the years. So when we had just 1 telescope up to 2009, we have a sensitivity that was, okay, not bad, but in comparison with now, it was terrible. We recently analyzed other mono data we had in this period. And of course, it's a little bit frustrating when now you can work with such a good sensitivity that is here defined by the red line. This gain in sensitivity was made not only because we now have 2 telescopes, but also because we worked a lot on the upgrade of the first telescope and also of the second one. An upgrade that involved not only the photomultipliers of the camera, but also other parts of hardware like the DIQ and also part of this upgrade, not in the picture I'm showing you, but in general, an upgrade was done also from the software point of view because MAGIC analysis chain now is very refined, so we are able to decrease the threshold even below this 50 using a special Monte Carlo that are related to a particular source we want to analyze. We can also go to a threshold of 25, and this was done for analyzing the Crab pulsar, and we are trying to, of course, improve these possibilities with MAGIC. The energy of the detection. You can detect a particle. Yes. Because it's deabsorbed by the extragalactic background light. By you studying the extragalactic background light, you are able to create a spectrum intrinsic, I mean without the deabsorption, and to compare this spectrum with the observed one. Yes, of course. Yes. Yes, yes. It also, this is the best threshold that we can have, talking only about the hardware, but with the software we can do more. And for the results I will show you today, we worked with other instruments to have multi-wavelength observations of the source I will describe later. So we were working with a lot of multi-wavelength collaborators, and we used all the data from these telescopes. And the one that is, we can say, closest to MAGIC in the energy bands is the Fermi, the LAT on board of Fermi satellite, that is working on high energy astroparticle. So it is overlapping a little bit MAGIC band, but it's a perfect partner for us. And sometimes we just follow triggers from Fermi to analyze a source in very high energy. Okay, now I will talk to you about the farthest ever detected source in very high energy. And this gravitationally lensed complicated name source, I will just say S30218. This source was detected by MAGIC last year, and it was a very complicated detection because, okay, we detected the source, but then analyze it was complicated because the morphology of a source so far away in very high energy, in the very high energy band, is not very easy. But anyway, it was detected before by Fermi. Here you can see the morphology described by the Merlin array, and also a nice picture from the Hubble telescope. What is going on here is a gravitationally lensed blazar. So what we see is the light not only of this source, but of the AGN that is in the middle between us and this source. What we get here, the redshift is 0.94, and it's gravitationally lensed by a probably spiral galaxy that is a redshift 0.68. You can see the Einstein ring in radio, and the separation of images is of this 0.33 arc seconds. These are just some feature of the source. And about gravitational lensing, you probably already know what we are talking about. But what is going on is that we have our telescope here detecting the source, but between us and the source, there is another big galaxy, in this case at 0.6 redshift. And so what we see is lensed by this AGN in the middle here. Here there is another description. You can see that having this galaxy here makes the changing the detection of the faraway sources. Like we have a lens in the middle, and then what we see is shifted respect to the real position of the source. Well, when we have strong lensing, we can see Einstein's ring, or multiple images with different magnification and timing. Sometimes we also can have micro-lensing effect, but this is more complicated, and in this case we were just working on the gravitational lensing. And so we detected this source follow up a Fermi trigger, and we had a detection of 5.7 significance. That for us is a short detection. Of course, it was compared with different analysis and cross-checked and everything. And so with this discovery, we say discovery in our energy range, of course, because this galaxy was already discovered by other instruments. We expanded our very high energy sky from 0.6 to 0.94, because the last source detected, the farthest one before this source, was at 0.6. We couldn't observe, yes, what maybe I didn't explain very clearly is that when you have gravitational lensing, you have a delay on the flare. You have the sources flaring, but since you have this lens in the middle, you can see two flares, the original one and the delayed one. In this case, we didn't see the original one that was seen by Fermi because we were in moon time, and for us it was impossible to see anything. But we could see the second one that was predicted at almost 11 days after the first one. So it was very exciting because Fermi was telling us, guys, we should see something in 10 days or so. And we were like ready to trying to spot the second flare. And when we did, it was great, but also a little bit disappointing because we could see the second one, but imagine if we could have seen the first one. It probably was a huge flare in very high energy, but we didn't see that because of the moon time. Magic telescopes can't work with moon time. We can work, but we couldn't in this case. And anyway, when we have a strong moon, it's not easy to analyze the data. It's very complicated. But okay, we catched just the second flare, and we were quite happy anyway. And here you can see the multi-wavelength we built with other instruments in X-rays and also with this other telescope, the KVA. All these data are preliminary because we are still working to analyze better the source, because we don't want just to say we detected for the first time. We want to analyze the extragalactic background light. And it's quite complicated because it's very far away for us, as I already told you, and we need the special Monte Carlos to do that. So the analysis is going to be completed, but anyway, that are still very preliminary. Okay, sorry, I jumped to the other source. Okay, now I will talk about the other source we recently discovered with redshift very close to 1. And the results were just accepted in the Astrophysics journal letters. We are again at redshift 0.939, so very close to the other redshift of the previous source I was talking you about. And here we could reach a threshold of 40 GeV using special Monte Carlo for this source. And we had a very huge detection of 25 sigma. So also we were very happy with this result. And you can see again here the multi-wavelength light curve for this source with all the instruments that we used to compare our data. We have seen similar pattern in X-rays, optical, and high energy. And we could distinguish 4 different periods when the flux was slightly different. And so we worked on 4 different periods for this source. We didn't see any intranight variability, but we have seen like a possible hint of 6 days or so. And here the broadband spectrum, you can see here the well-known shapes of the spectrum of this kind of AGNs. We have the first one here, and the second peak, and in gray you can see from the archival data, and if you compare with the observed data, you can see there was a big shift in energy, and this was very interesting for us, and also the behavior of the source resembles another outburst seen from another source we are analyzing with MAGIC. And we also could constrain the emission of the jet working on this broadband spectrum just outside the broadline region. Of course, it's not a huge changing in what it was predicted for this kind of source, but anyway, we were happy because for the first time we could probe a source so far away. And we also had a 9 degree of optical polarization that could say that the emission may come from a compressed region in the jet. We cannot say more right now. Also, we constrained the extragalactic background light. That this was for us a very important result because for the first time we could work on the extragalactic background light so close to the limit of the gamma ray horizon. Here you can see okay, actually these plots are not preliminary anymore because are in publication, but anyway, you can see the spectrum observed, this blue one, and the absorbed one. This spectrum in red is the spectrum without the ABL absorption. And also, we got a nice upper limit on the opacity. That okay, here is 1.73 for the Dominguez model. That is one of the most famous models we can use to constrain the extragalactic background light. Okay, so conclusions. We can detect for the first time very high energy emission from these 2 sources, not only PKS but also the gravitationally lensed. The redshift that is very close to the limit of the gamma ray horizon. And we are studying these sources, allow us to understand more about blazars when the universe was only half of its current age. And we also constrained the extragalactic background light. And now we demonstrated that with MAGIC we can reach such a lower threshold and high sensitivity that we can really go behind the gamma ray horizon and try to push the boundaries beyond the 1. We are trying to do that. We are working on this, and we are also working on recalculate the gamma ray horizon, introducing these new sources, because as you have seen in the beginning of the presentation, here we can calculate the gamma ray horizon using sources that are close to 1, and in this way have a better idea of what are our limits in very high energy astroparticle physics. And okay, this is what I wanted to tell you right now, just to tell you what MAGIC is doing. We are doing a lot of things also if our group is a small one, and maybe we are involved in several different experiments. And if you want to know more about MAGIC, you can visit us in our social media pages. Thank you so much.
Thanks, Marina, for the talk. Questions?
I want to know the models you were showing in the SAD. Which type of model are you using to model that?
Yeah. I will show you this spectrum for, it's okay, this one. We use Dominguez for, you mean
No,
for
I mean the previous slide. This one.
Here, yeah. We are using our collaborator Fabrizio used to model this data, an internal Compton scenario model that I don't know the details, but is based on the internal Compton analysis of the broadband spectrum. Is Fabrizio Tavecchio, yeah, is our
Well, it's a basic question because we don't get many talks about high energies. So what's the angular resolution that you can work at to define your source? How well can you know that you're pointing at, that you've received gamma rays from one source or another?
Well, you mean the highest resolution in this case, we can talk about different parameters, you know. It's not easy to compare between different sources, but talking about AGN, for example, the redshift is a nice parameter. We can say if we can detect a source that is around 1, like we did, we are really doing our best, you know.
But do you have some kind of error box and you can say the source must be within
Okay.
just the angular discrimination?
Okay, the angle discrimination, okay. We have an angular resolution that is 0.1, that for other telescopes is probably nothing, but for the Cherenkov imaging telescope, it's very good actually. What we can do is study the morphology. Degrees. Yeah. What did I say?
No, just you said 0.1.
Okay, sorry. Yeah, no, I thought I say other things like radians, so that's what I'm saying. And so, yes, for us, that is very good. Yeah, it's enough to study the morphology or some faraway sources, and also to try to investigate globular clusters and other more complex sources.
Yes, because I remember the early days of radio astronomy when the resolution was something like that, and obviously in your case there are candidate sources and there won't be any other source in the box, so you say it's that source, but it must be quite complicated, I should think.
Yeah, it's also a little bit frustrating, but but anyway, it's also very exciting because it's like we are seeing that in front of us there are opening a lot of possibilities. And also, what is true is that now another very big experiment, the CDA, will come in La Palma with a lot of telescopes. Then MAGIC, okay, will not be so important then. So we're trying to push everything right now before CDA comes and steal from us everything.
Okay, thanks. Good.
Nacho.
Two questions then. One connected to the previous one. So with the new array of telescope, what would be the new resolution in area?
My colleague Monica can tell you, because she will be strongly involved in CDA. Now I don't remember the angular resolution. Now I don't remember.
Arc seconds. Wow. Okay. So my question connected to what you were saying. So you say that when you are exploring the interaction of the gamma ray photons with the extragalactic light, the background light, you said, So if I understood you well, you're saying that you have interaction of gamma ray photons with photons in the optical and in the near infrared.
In the UV, this extra...
Well, but in that
Yes,
range,
okay,
optical
sorry,
range or
sorry,
so. So how many interactions do you typically expect? So do you know that? So
How many interactions? No, I never thought about this in these terms. Because what I'm thinking about, what is in my mind, is the difference of the spectrum index before and after this, the absorption. But now this very nice idea of how many interactions now I can tell you. No, I will go and have a look because of course it's a good way to describe the absorption.
just to have an idea of the number density.
Yeah, you're right.
Any other question? No? Okay, so let's